instead of trying to reconnect.
Oh, God. No.
Stand by.
Good afternoon. I'm Andrea Messer, Senior Science Writer at Penn State, and this is our Facebook Live event with Michael Mann, Distinguished Professor of Meteorology. We'll be talking about climate change, and Michael will begin with a discussion of the last 14 months of warmest average global temperatures. We'd like to answer as many of your questions as possible on the topic of climate change, but please keep the conversation respectful. Mike?
Thanks. Well, it's a pleasure to be doing this event today. And it's we're in the midst of a heat wave right now here in the eastern U.S. In midsummer. And that is indeed part of a larger pattern where we have seen record-breaking temperatures now for more than a year. Every single month, or just about every single month over the last year, was the warmest month of that month on record. That is part of a pattern where the last decade has been the warmest decade on record for the globe, and the Earth has warmed up about 1.5 degrees Fahrenheit over the past century. So people sometimes ask, can we relate individual record temperatures to climate change? And in fact, my co-authors and I published an article earlier this year in the journal Nature Scientific Reports, where we actually looked at that question. We looked at the fact that 9 of the last 11, and I think 11 of the last 13 years have been the warmest on record. And we looked at whether or not that was likely to arise by chance, or whether we could only explain this very large number of record-breaking temperatures over the past decade and a half when we take into account human-caused climate change, the warming of the planet due to greenhouse gas increases from fossil fuel burning and other human activities. And what we found was that the likelihood of this sort of onslaught of records happening by chance alone was somewhere in the range of 1 in a million. Extremely unlikely to have happened from chance alone. And when we take into account the human-caused warming of the globe, we find that those records were actually relatively likely to have occurred, anywhere from a 50 to 70% chance. So when we look at individual record temperatures, whether it's a record warm spell in the United States or whether we tally up sort of the number of record breakers, if you look at how often we break all-time records for heat in all of the locations around the United States where we have measuring stations, it turns out that we're seeing twice the number of extreme temperature all-time highs. Twice as many as we saw a century ago. And we can't explain that without human-caused climate change. The fact that wildfire in the western U.S. has tripled over the past several decades, we can only explain that when we take into account the warming, the increased drought, which in part is a result of the warming and increased evaporation and earlier snowmelt from the mountains. When we look at the number of 1,000-year floods that by chance shouldn't happen any more often than once in 1,000 years. And we've had several of these just in the last year in Texas, in South Carolina. We cannot explain these extreme weather events without taking into account the human-caused warming of the globe. And so I often point out that when it comes to the impacts of climate change, we can actually now see them playing out. We see the impact of human-caused climate change in many of the extreme, unprecedented weather events that we're seeing here in the United States and around the world. So climate change, its impacts are no longer subtle. We are seeing them firsthand in our daily experiences with our own two eyes.
Okay, first question. Alex Warner asks, why do core samples show that temperatures during the Middle Ages were hotter than they are now?
I'm not sure what the caller is referring to. There are various types of cores. There's sediment cores, deep sea sediments and lake cores. There are ice cores that we use to try to reconstruct past climate patterns. In fact, much of my work in the past has related to the use of so-called proxy records, things like tree rings and ice cores and corals and sediment records that we can use to piece together the puzzle of how the climate changed in the more distant past, because we only have about a century and a half of widespread instrumental thermometer measurements to measure the warming of the globe. If we want to put the modern warming in a longer term context, or if we want to put drought patterns or any climate phenomenon in a longer term context, then we have to use these paleoclimate archives that allow us to build up a picture of how climate changed back in time. And when we do that, there's pretty much now a universal consensus then when you take all of the data that are available around the globe and you use them to reconstruct the average temperature of the Earth or the average temperature of the Northern Hemisphere, the current warming, the current 30-year interval is the warmest such interval in at least 1,000 years, and possibly much farther back than that, although we don't have as much data when we go farther back in time. But we have fairly widespread data going back more than 1,000 years. And when you take all of that data into account, for example, the most recent report of the Intergovernmental Panel on Climate Change, the IPCC, which consists of hundreds of scientists around the world who assess sort of the state of the art in our understanding of climate change and summarize that in a report under the auspices of the United Nations that comes out every 5 to 6 years or so. In the most recent IPCC report, they concluded that it is likely that the current 30-year interval is the warmest such interval in at least 1,300 years, and probably farther back in time. There are some regions where temperatures were somewhat warmer than other regions in the past, because you have phenomena like El Nino or changes in the pattern of the jet stream that take place, changing atmospheric circulation patterns, which lead to some regions sometimes cooling while other regions warm. And there are some regions where temperatures 500 years ago might have been nearly as warm as they are today. Regions in the North Atlantic, neighboring Greenland and Eastern North America, Western Europe. There is a region in the North Atlantic and neighboring localities where we think temperatures were relatively warm 500 years ago, but the rest of the globe was quite a bit cooler. And when you average all those data, what you find invariably is that the recent warmth really has no precedent as far back as we can actually go confidently.
Tom Nelson asks you to name one example of a carbon dioxide-induced unprecedented weather event.
I'm not quite sure how to interpret that question. By carbon dioxide induced, I assume that the individual is asking about human-caused climate change, and can we actually attribute individual extreme weather events that have been observed in recent years, for example, to human-caused climate change. There's actually a very large emerging body of work using methods that are called detection and attribution methods. And what they do is they'll take a climate model, a theoretical climate model, and they'll run that climate model under industrial conditions when CO2 concentrations hadn't yet been elevated from fossil fuel burning. and then they'll run the model again at modern CO2 concentrations. And they will see how often a particular event happens in both of those cases. So, for example, the record flooding in the UK a few years ago, there was a study published in one of the leading journals, I think it was the journal Nature, where they actually looked at that record flooding event and how often it happened in a pre-industrial climate versus how often it happened in their model when they increased the level of greenhouse gases to modern levels. And they found that there was a very substantial increase in the likelihood of that event happening now relative to pre-industrial time, enough of an increase that they could do what they call fractional attribution. They could say that there's a 70 or 80% chance, something in that range, that this event can be attributed to human-caused climate change. So there is a way to try to specifically seek out whether or not there is a fingerprint of human-caused climate change in any particular event. But what we typically do is we step back, and rather than looking at individual events, we look at the statistics of those events. How often are they happening? And when we look at, again, extreme heat in the U.S., extreme wildfire, unprecedented flooding events, what we find is that there is a substantial increase in the occurrence of these events such that they would not have happened at the frequency that they're happening in the absence of human-caused climate change. There is increasing confidence that we can, in that sense, attribute the increase in many types of extreme weather events to human-caused climate change.
Alex D. would like to know what's the difference between ozone and CO2 in the atmosphere, and how do they affect climate change?
It's a really good question because it gets at a number of interesting interrelated issues. Sometimes people will ask, ozone depletion and global warming, are these related? Are these the same issue? And by and large, they're not. The depletion of the ozone layer caused by chlorofluorocarbons, CFCs, and other materials, industrial materials, that emerged really in the 1970s and worsened in subsequent decades. That was indeed caused by the loss of ozone due to chemical reactions with these constituents in the stratosphere. And we saw a substantial loss of the protective ozone layer, in particular in the southern hemisphere, in the polar regions of the southern hemisphere. So technically speaking, ozone depletion is a different environmental problem from human-caused climate change. Now, here's where things get interesting. Many of those chlorofluorocarbons that deplete ozone in the stratosphere also happen to be greenhouse gases. And because they're greenhouse gases, they warm the planet, just like carbon dioxide from fossil fuel burning warms the planet. So if you look at the various policies that have been enacted, back in the 1980s, we passed the Montreal Protocol to ban many of these substances, these chlorofluorocarbons that were depleting the ozone layer. Now, it turns out that that is the one piece of policy, the one policy instrument that has made the biggest dent in the global warming problem so far, because those same materials, those same CFCs that were depleting the ozone layer are also greenhouse gases, and they were warming the planet as well. So it's an interesting insight into, first of all, that it is possible to solve global environmental problems through policy measures. There was an article published just within the last week in the journal Science, I believe, showing that we have now seen a very substantial recovery of the ozone hole due to the passage of the Montreal Protocol in the 1980s. Signifying the fact that we can, in fact, solve global environmental problems, be they ozone depletion or global warming, through concerted action, through treaties between nations that seek to stem the production of various pollutants that are impacting our environment.
Steve Noralski, I hope I got that right, asks, aren't the projections without global warming for a global cooling trend?
Yeah, it's a really good point. In fact, that's correct. If we were not warming the planet by increasing the concentration of greenhouse gases in the atmosphere, the same climate models that we use to study the impact of increased greenhouse gas concentrations tell us that natural factors like volcanoes and small but measurable fluctuations in the brightness of the sun, those natural factors actually changed in a way that should have led to cooling over the past half century or so. We've seen a number of large cooling volcanic eruptions in recent years. That's a cooling effect. We've seen a small dip in solar output in recent decades. That too is a cooling effect. So if you look at the natural factors alone, the globe actually should have cooled slightly in the latter half of the 20th century instead of doing what it did, warming dramatically. That's important because people will sometimes ask the question, how much of the warming that we've seen is due to human-caused increases in greenhouse gas concentrations? And the true answer to that question is that more than 100% of the warming that we've seen is due to increased greenhouse gas concentrations. What I mean by that is that in the absence of a human impact on the climate, the globe should have cooled slightly in recent decades. And so we overcame a natural cooling trend to warm as much as we did. We literally warmed the planet more than the warming that is due to us is literally more than 100% of the warming that we've seen, because it also includes the fact that we stemmed this cooling trend to begin with and then warmed on top of that.
Josie Smelko says, how does climate change explain some of the record lows a few years ago caused by the polar vortex?
It's another really good question. So, if we step back and we sort of look at the big picture, we see a dramatic increase in the number of record highs relative to the number of record lows, where that ratio is roughly doubled over the past half century, which is what we expect. As we continue to warm the planet, we expect to see more record highs and fewer record lows, and that's what we're seeing. And in fact, what we're seeing closely mirrors what the climate models predict should be happening. That having been said, there are some regions where we have seen some unusually cold weather that was unusual enough to lead scientists to ask, if we step back a little bit more and we look at this at a more granular scale, is it possible that in some regions we're actually seeing an increase in conditions that can lead to extreme cold, say in the eastern U.S. During the winter? And there's an emerging body of work. There's still a pretty robust debate within the scientific community, and it's a worthy debate. It's a real debate. It's not like the fake debate about whether human-caused climate change is real. Scientists aren't seriously debating that. But scientists are debating things like, are we perhaps influencing the pattern of the northern hemisphere jet stream in a way that could lead to weather extremes like the extreme cold that we've seen in the eastern U.S. In certain winters, certain recent winters? Well, that extreme cold in the eastern U.S. was part of a larger pattern of the jet stream that saw unusual warmth in the western U.S. And the Pacific Northwest and Alaska, and saw a jet stream that veered north of where it would normally go along the west coast of the U.S., depriving California of the moisture it depends on in the winter. And that's why California has seen this unprecedented drought over the last decade. It's a combination of unusual warmth and more evaporation of soil moisture, but also the fact that the jet stream has tended to veer northward of California, depriving it of the rainfall and the snowfall that it would normally get. And there is an emerging body of work that suggests that that particular pattern of the jet stream might actually be favored by human-caused climate change through a mechanism that is somewhat subtle. It has to do with the melting of the Arctic sea ice. And the Arctic sea ice is actually disappearing at a rate that's faster than what the models predict. We're seeing right now, this summer may see potentially a new all-time low. And we are seeing the loss of Arctic summer sea ice occur faster than the models predict it to, which means that many of the impacts of that melting sea ice may be further along than what the climate models predict we should be seeing at this point. Among those potential impacts is a change in the pattern of the northern hemisphere jet stream. And again, this is still fiercely debated in the scientific literature, and there's scientists with the differing views on this matter, but there is a body of scientific work that suggests that when you melt away the Arctic sea ice and you expose the Arctic atmosphere to those relatively warm waters, the ocean underneath the sea ice is quite a bit warmer than the cold air on top of the ice. So when you get rid of that sea ice, you allow more sunlight to warm the ocean, you allow more of the heat to escape from the ocean into the atmosphere. Well, it's actually the heating of the atmosphere vertically that determines the pattern of the jet stream. And an emerging body of work suggests that all of that heat that may be escaping from the Arctic Ocean into the Arctic atmosphere may change the pattern of the jet stream in a way that actually favors that unusual sort of undulation where the jet stream goes far north of California up into Alaska, giving it warm winters, giving California dry winters, and then it crashes down in the eastern U.S., bringing all that cold Arctic air into the eastern U.S. And giving us extremely cold conditions. Not record cold. We're not seeing record cold temperatures in recent winters, but we're seeing temperatures that are colder than we might expect. And some scientists think that it may have to do with this mechanism. And so this is just another example of how there is uncertainty in the science. There are mechanisms that we still don't understand completely, but that uncertainty is not a reason for it's not a reason to dismiss the seriousness of climate change. It may actually be a reason to be more concerned about climate change because there are potential impacts that are happening now or looming in the future that could actually be in excess of what the climate models are currently predicting. If you look at the track record, if anything, our climate models have tended to underestimate many of the impacts that we're seeing. The rate of loss of sea ice in the Arctic, the loss of ice from the major ice sheets, which is contributing to sea level rise that's happening faster than we would otherwise expect it to. There's a theme here, which is that uncertainty in the science is not a reason for inaction. It may actually be a reason for even more concerted action because of the possibility that the changes could be substantially more risky than we currently estimate them to be.
Garcia Pedro Hala Madrid asks, since science is not about consensus, can you explain if the current position of the continents is a key factor to keeping the South Pole cool, and thus it's very unlikely that under the current position and the direction of ocean waters, the South Pole will not do what the media is advertising?
I'll try to parse that question as best I can. First, the question of consensus. Science actually does operate through a process of consensus, but the consensus that we're talking about isn't a bunch of people standing in a circle and holding hands and agreeing. It consists of replication of findings by independent teams of scientists who publish their results in the peer-reviewed scientific literature, and those results are subject to scrutiny by other scientists who can comment on them. There is a give and take that takes place within the context of the peer-reviewed scientific literature that was characterized. It's part of what Carl Sagan, the great Carl Sagan, once characterized as the self-correcting machinery of science. The wonderful thing about science is that it has this self-correcting machinery. If scientific thinking goes down a dead end, if it goes in the wrong direction, then ultimately that will be discovered because independent scientists will be unable to verify a conclusion. They'll come up with a different conclusion. They will subject that conclusion to the independent scrutiny of their peers. And that's the machinery that keeps science moving in the direction of a better and better understanding of the natural world, despite the fact that there are sometimes scientific dead ends and wrong turns. In the end, that process leads us inevitably towards a better understanding of the world. And that is true with plate tectonics. That process has led now to our understanding that the plates move around, the continents move around. It has led to the miraculous, seemingly miraculous medicines that we have now, the technology, GPSs that we have in our cell phones. All of this is built on scientific discovery and the process of consensus that is arrived at through the give and take in the scientific process, the give and take in the peer-reviewed literature, the give and take that takes place at scientific meetings where scientists present their findings and other scientists can challenge them. That's the process of consensus, and it depends on a consilience of multiple lines of evidence established by independent teams of scientists that all lead in the same direction. With climate change is no different. There is quite literally about as strong a consensus within the scientific community that the globe is warming and that human activity is responsible for it, a substantial part of it. It may be all of it. That is a conclusion that is where there is about as widespread a consensus as there is with any proposition in science today. And that sort of should be the starting point for discussions of policy. There's a worthy debate to be had about the policies to deal with climate change, but there's no longer a worthy debate to be had about whether the problem is real. There is, again, about as strong a consensus, a scientific consensus, with that proposition as there is with anything in science.
Since tree rings failed to match temperatures recently, how can you be confident they accurately match past temperatures?
Oh, that's an interesting question. It's not quite correct, the premise of the question. There's a certain type of tree ring information. Most tree ring data are derived from the growth thickness. How much growth is there? How thick is the ring? Typically tells us about, the growing conditions. And in a region where trees are, say, stressed by temperature or stressed by rainfall, where that's a limiting factor in the growth that the tree exhibits in a given year, then the ring thickness often provides a fairly good proxy for how temperatures or rainfall changed in the past. It's just one of a large number of types of proxy information, along with ice cores and corals and sediment cores and what we call speleothems, basically stalagmites and stalactites. There is a vast array of different types of proxy data that we use to build up a picture of how the climate changed in the past. And that picture is much stronger than it would be if we relied on any one type of information like tree rings. And with tree rings, again, with the growth thickness, which is the primary variable that's used from tree ring data, there really isn't any evidence of any fundamental change in its relationship with climate. Now, with the density of the wood, which is another variable that some scientists have used to estimate past temperatures, there is an interesting phenomenon known as the divergence phenomenon, where that particular variable, the density of the late wood, the wood that's put on at the end of the season, towards the end of the season, the density of that wood is a proxy in many circumstances for summer temperatures. And that particular variable seems to have sort of ceased in tracking the overall warming of the globe as well as it had in prior decades, somewhere around 1960. There are some scientists who published about this problem. And again, it gave rise to the term the divergence problem back in the late 1990s. And tree ring specialists have become interested in that phenomenon and trying to understand what may be going on. And there are various competing theories for what's going on. Some of them have to do with the fact that atmospheric pollutants may be influencing the trees in some way that's changing that relationship that had existed previously. There are a number of hypotheses that have been put forward and which scientists are debating. So actually, there's no shortage of explanations. If anything, there are too many explanations, and scientists are trying to sort them out. But in the end, does it have any implications for the big picture? No, not really, because first of all, it's only tree rings. It doesn't pertain to other types of proxy data. And it's only a particular type of tree ring information, tree ring density, which isn't even the most prevalent variable that tree ring specialists use to reconstruct past climate. So there is interesting science to be done in understanding things like the divergence problem, but do they fundamentally impact our ability to assess past temperature changes and how they compare with temperatures today? No.
I'm going to ask my question. Richard Alley talks about tipping points, and I was wondering if we've reached a tipping point in climate change, and if so, is this the first of many? And are you at all optimistic about your ability, or our ability, to deal with climate change?
Okay, well, great questions. First of all, with respect to tipping points, people often ask me, where is the tipping point? How much warming of the globe do we need before we see the tipping point? And the answer is there is no one tipping point. As you allude to, there are potentially many different tipping points, and some of them we've probably already passed. There is an emerging body of research that suggests that we have probably warmed up the climate, warmed up the southern oceans enough to destabilize the ice shelves that support a substantial part of the Antarctic ice sheet, a large part of what we call the West Antarctic ice sheet, which is the low elevation part of the ice that's basically in contact with the ocean and is most susceptible to melting. And we may now have passed, in essence, a point of no return where we've warmed up the ocean enough that we will destabilize those ice shelves and lose enough ice to give us, maybe 10 feet, 11 feet, 12 feet of sea level rise, no matter what we do. That ship may have sailed. Now, we don't know how quickly that might happen. It turns out that the controls on how quickly we will lose that ice involve some pretty complicated ice physics that scientists are still working out. And so some scientists think that it could take many centuries before that would play out. Other scientists think there's the possibility it could play out more quickly, again underscoring the fact that uncertainty isn't necessarily our friend. There are scenarios where this could happen faster, considerably faster than we thought. That's a tipping point, though, that we may have crossed. Another tipping point, which we might be close to, is the collapse of the so-called conveyor belt ocean circulation pattern that was sort of popularized in the movie The Day After Tomorrow. It's this warm current that travels northward into the North Atlantic and keeps regions like Iceland and parts of Western North America, Western Canada, or Eastern Canada and Western Europe warmer than they otherwise would be. There is very strong evidence that ocean circulation pattern collapsed toward the end of the last ice age, and that was due to the fact that all this melting ice rushed into the North Atlantic in the form of fresh water. That fresh water formed a light cap on the ocean because fresh water is less dense than salty water, and that cap prevented the sinking motion that helps drive that ocean circulation pattern. And it essentially collapsed, and there was a return to Ice Age-like conditions in parts of the North Atlantic because of that. There is the possibility that we could see a sort of weaker version of that because of global warming, and work that my collaborators and I have done, a paper we published in the journal Nature Climate Change last year. We showed that may already be happening. There's this phenomenon referred to as the cold blob. There's this area in the North Atlantic right now where surface temperatures were the coldest on record last year, during a year that saw the warmest temperatures on record for the globe and the warmest temperatures over the world's oceans. There was one region in the North Atlantic that saw its coldest temperatures on record. And that blob of cold water has the signature of what we predict with a collapse or a slowdown, in this case, of this conveyor belt ocean circulation pattern. The climate models say that we shouldn't see a substantial reduction until later this century. My co-authors and I argue that we're already seeing it. Another example of a change in climate that may be further along than the models have predicted. There are many other possible tipping points. Some of them have to do with methane that's trapped in the permafrost and along the coastal shelves of the oceans. With warming, that methane could be released into the atmosphere. Methane, in some respects, is an even more potent gas, greenhouse gas, than carbon dioxide. So if that were to kick in, we would suddenly see a substantial additional release of greenhouse gases into the atmosphere that could accelerate the warming. We don't know how close we are to that tipping point. There are many other tipping points that loom out there. We can be certain of that. What we can't be certain about is how close we are to them. And to me, it's sort of like mines in a minefield. The only way to avoid stepping on them is to not step out onto the minefield. And in that sense, the only way to be confident that we will avoid crossing these tipping points is to not venture any further out into the minefield through our continued burning of fossil fuels and the increase in greenhouse gases resulting from that. And then the latter part of your question was about optimism. So you might be listening to me thinking there are all of these impacts that many of which are playing out even faster than the climate models say they have predicted. The problem in some respects seems to be even worse than what the scientists had predicted. You might be thinking it's hopeless, that there's nothing that we can do, but nothing would be further from the truth. The good news is that there is a general sense within the scientific community that if we can keep warming below roughly 2 degrees Celsius, 3.5 degrees Fahrenheit warming of the globe relative to pre-industrial time, we can avoid many of these tipping points, many of the most dangerous and risky climate change impacts, if we can keep warming below that level. And in Paris this last year, with the latest climate summit, nearly 200 nations from around the world agreed to reductions in carbon emissions that won't keep us below that 2 degrees Celsius danger limit, but will bring us about halfway from where we would otherwise be headed, towards 5 degrees Celsius, 9 degrees Fahrenheit warming of the globe by the end of the century, something that by all estimates would be catastrophic. The commitments that were made in Paris are enough to take us from there halfway down to that 2 degrees limit. And what that indicates is that if we can continue to build on the substantial progress that we've already seen with global carbon policies regarding global carbon emissions, that there is a path we can see where we do achieve, through additional negotiations and increased incentivization of renewable energy policies to encourage, to accelerate the transition away from fossil fuel burning, there's a path forward where we do in fact avoid that dangerous 2 degrees Celsius, 3.5 degree Fahrenheit warming of the globe. There's still time to make sure that our legacy is not to leave behind a fundamentally degraded planet for our children and grandchildren. And so I am cautiously optimistic, not only that there's still the chance of avoiding such dangerous climate changes, but that we will choose that pathway and we will rise to the occasion, as we often have as a species, and make the changes necessary to avoid that dangerous warming of the planet.
And on a similar note, Michelle Chandler wonders if you have formulated a sort of top 5 or 10 list of behaviors that have changed widely enough right now would do the most good.
Thanks. Well, if I'm not mistaken, that may be, I think that's the Michelle Chandler, who was a friend of mine from high school, growing up, Amherst Regional High School. And she always, I seem to recall she asked great questions back then as well. It's a really good question. What are the practical things that are happening, on the ground that are making a difference? One of them is sort of policy at the global level. These global negotiations like the Paris Summit that are sort of taking us in the direction that we need to go. But much of the progress is actually happening at a much smaller scale, sort of at the grassroots level, where you see organizations like 350.org, led by my friend Bill McKibben, that are really sort of galvanizing public support for incentivizing clean energy and instituting policies to put a price on carbon, to keep the carbon in the ground so we can avoid dangerous warming of the planet. We see a lot of progress at the municipal and state level. Right now, we have a situation where there are very poor prospects for any comprehensive climate legislation to come out of the current U.S. Congress. But in the absence of sort of congressional leadership for climate action, we are seeing states banding together. The West Coast states of California, Oregon, and Washington have formed a coalition to put a price on carbon emissions. The New England states have banded together to form a similar coalition that's known as RGGI. There's some speculation that Pennsylvania could potentially become part of that coalition. But right now, if you tally up the population in those states that are already part of a coalition to put a price on carbon, a market signal that helps us accelerate the transition away from fossil fuel burning to renewable energy, if you tally up the people in those states, it's close to 30% of the population. 30% of the American population is in a state where there is a policy now in place to put a price on carbon and to move us in the direction that we need to go. We're seeing many of the largest cities passing policies, instituting policies to reduce carbon emissions, to incentivize renewable energy. We're seeing the rest of the world really move ahead. Ironically, there's the danger that the U.S. could fall behind. Right now, countries like Germany are getting something like 30% of their power from renewable energy. The global average now something like 20% of global power is derived from renewable sources. That's a huge increase from what we saw just a few years ago. In the U.S., it's only about 15%. So we're actually somewhat behind the global average right now. Of course, with the Clean Power Plan that has been instituted by the current administration and other policies instituted by the EPA to, for example, improve vehicle transportation efficiency, fuel efficiency standards. We do see prospects for the U.S. now moving ahead substantially, and we're seeing a tremendous increase in the amount of power. Here in Pennsylvania, we're able to purchase our power entirely from wind. We're seeing huge increases in solar power and wind power in states like Texas, California. So the changes are all in the right direction. We're sort of turning the corner in really in meeting the challenge of acting to avert dangerous climate change. But we need to turn the corner even faster if we are going to avert truly catastrophic climate change. And so, again, we have to do even more than we're doing, but there are a lot of signs now at the local level, at the state level, at the national level, at the international level, that we're starting to move in the direction that we need to be moving in. And again, that's part of the reason that I am cautiously optimistic that we will rise to the occasion and meet this challenge head on.
I have one last question, and it's an interesting one. What's the optimal global temperature? Why should we believe that cooling is better than warming?
So the optimal global temperature would be the global temperature that we have adapted a civilization of 7 billion people to. We have built this massive infrastructure that supports 7 billion people on the face of the planet, moving towards perhaps 9 billion by the end of this century. And that infrastructure is quite fragile. And we've seen examples of how fragile that infrastructure is when we have disasters like Hurricane Sandy or Hurricane Katrina or the California drought. We see how fragile that infrastructure really is and how dependent we are on the climatic conditions that we built this civilization in and on, remaining as they have been over the period of the last 10,000 years during which human civilization developed, modern human civilization developed. So any change in climate that moves us away from the conditions that we're adapted to, which are the conditions really that existed prior to the Industrial Revolution climatically, any changes that lead us away from those conditions are a threat. And the faster those changes take place, the greater the threat. Right now, we are increasing the concentration of greenhouse gases in the atmosphere at a rate for which there is no precedent in the geological record, as far back as we can go. No evidence of increases in greenhouse gas concentrations as rapid as those that are taking place today due to the extraction and burning of fossil fuels. One way to think about it is, 100 million years ago, there was a lot of CO2 in the atmosphere. Dinosaurs roamed the planet. It was a very warm time. There was no ice. And geological processes related to plate tectonics and chemical weathering slowly took that CO2 out of the atmosphere and deposited it below the surface over a time frame of 100 million years. Now, all of that carbon that got buried over 100 million years is what we call fossil fuels. And what we're doing right now is extracting that carbon and putting it back into the atmosphere, not over a time scale of 100 million years, but over a time scale of 100 years. Faster than anything we see in the geological record. And it is very likely that if we continue on that path, we exceed our adaptive capacity and the adaptive capacity of other life on Earth. Life simply did not adapt to, did not adapt to changes that occur on such a rapid time scale. And so the threat isn't the absolute level of warmth of the planet, but how quickly we are moving the planet away from the climate that we and other things, other living things, have adapted to over many, many thousands of years.
We've come to the end of our time. I hope you've enjoyed our Facebook Live event. Thank you to all who asked questions, and I'm sorry that we couldn't answer all of the questions that were put forth. Hope to see you the next time we do an event.